Hello and welcome to this lovely video of the cod and chips formula derivation. Okay, so I thought I'd do one just, to help everyone or whatever. And I've got a new microphone. Okay, so if we can all remember or all have seen what it actually is, it is this thing here where it's the square root of 2 cod over chips. Now, for the exam, we don't need to know it, but I think it's good to actually see where it comes from, to be honest. So before we start, there's a couple of things, maths tools that people need to know. So if you have a number, and I mean people usually use x as a number, something we need to know is if we have something like x cubed and then we have x squared and then we have x to the 1, right? We need to know what x to the 0 is, okay? And x to the 0 is always known, or not known, sorry, but is just 1, okay? And the reason why is because if you have something like 2 cubed, yeah, and then 2 squared, well, what you're doing between 2 cubed and 2 squared, so 8 and 4, is you're dividing by 2, okay? So each time you go along, you divide by 2. So when you get 2 to the power 1, which is 2, 2 to the 0, you divide by 2, and 2 divided by 2 is 1. Okay? So that's our first mathematical tool to know. Okay, so I'm just going to write any number here, any number n to the 0 is 1, okay? The second mathematical tool is, I'm sure you've heard of it, is differentiation. And that is given by a notation that says d by something over d and then the variable which you want to differentiate. So actually in this cod and chips it's going to be q, okay, but we're not there yet. But anyway, what this means is if you have a graph like this and it's like straight line or wavy or whatever, and then it's like this, if this line is a formula, some equation, y equals x cubed plus x squared or whatever, and you differentiate that formula and you put in a point on your x-axis, say you plug in 3, you find the gradient of this line here at point 3. So as we can see, it's this line here, okay? So that's what you get by differentiating something. So I'll just give you a quick demo of differentiating something and then we can actually get into this derivation. So if I'm sure in school you've seen, oops, that's a bit large, isn't it? I'm sure at school you've probably seen things like y equals x squared plus 5x plus 3, okay? So to differentiate that, you do this dy by and dx. And so it's dy by dx because if you have a graph like this, and you've got y here and you've got x here, d basically means change. So if you have a line, just a straight line like this, dy by dx means how much does y change for 1 unit of x. So if it's a straight line, then let's say y equals 5x, So we can see every time x goes up by 1, y goes up by 5 times 1. So in each unit here, so this is 0.1, then y is actually here is 5, okay? And at 2, y is then 10, and so on, okay? So so anyway, we've got a formula here, okay? Y equals x squared plus 5x plus 3. So to differentiate it, let's get back to where we were. Dy by dx equals, so what you do is you times by the power of the variable. So in this case the variable's x, so it would be 2x, and what you do is you reduce the power by 1, okay? So it's 2x just to the 1 plus, now this 5x is to the 1, so 5x to the 1. So if we times by the power, so that's 1 times 5, and then reduce the power, so x to the 0. Now we know what something to the 0 is, it's just times 1. So this ends up becoming is just 5. And if it's a constant, what the rule is that just disappears, okay? So we end up with 2x plus 5. And that is our gradient on a slope, and we'll need that later. So let's get into the actual, cod and chips thing. Now we know the maths techniques behind it. So what we need to know is the total costs of, so TC, total costs of, and it's all to do with ordering inventory and how much inventory you're going to order in over the space of a year, okay? So you've got two things to think about when you're in terms of the costs of this inventory that you're ordering. So the first one is how much does it cost to hold all the units of your inventory that you have, and we'll say over the year, okay? So how much would that cost? And then we've also got, because we could just buy one batch of inventory for the whole year and hold it for ages, but we'll see why later on why we can't do that. Or you can keep ordering in this inventory, and that's going to be your cost of ordering. Your total cost of ordering. So because you're going to have to keep ordering in goods, as this year goes along. So that's our main, thing to think about, and I'll write this up here. TC equals holding costs, and costs of ordering, and it's the total. Okay. So what we've got to do is we've got to try and figure out about each of these individually. Okay, so I'll get rid of this. So we'll start with the cost of ordering. So in our cod and chips formula, we've got D, and D is demand. So how many items do people want over the year? Okay, so we've got Q. This is our main variable, and this is what we're going to be looking into a bit more in detailed. So Q is the total amount of goods which you're going to order in each time you order something, okay? So what we're going to do is this cost of ordering total, so I'm going to put cost of ordering, the total, right? That equals basically your demand, which is how much do people want over the year, divided by how many goods you're going to want to order in. So say your demand was 10, and each time you order 2, you end up having to order 5 times, because 5 times 2 is 10. So over the year, and then you times that by your cost of ordering, and that gives you your cost of ordering total. So here I'm going to write that one down just so we can keep that. Cost of ordering total equals demand over the goods we order times the cost of ordering. So that's our first thing to work out. Now the second one is going to be the holding costs. Now that's a bit more involved. So if we think of having an inventory, now what I'm going to do is I'm going to draw 2 lines like this. And actually, I won't go into this, but you have this buffer here as well, this buffer line, okay? But we'll just talk about this line here, and I'm going to write minimum, and then we'll have a maximum inventory as well, okay, that we want in. So say we start with, a maximum amount of goods over, and say this is at a year, okay? So hopefully, because we're selling these goods over time, we're selling. Eventually, we're going to get to a point where we want to reorder. So, just any point. We'll say this is, I'm just going to write average for now. Right. Anyway, so as we're going along, we sell, and eventually we're going to get to this minimum point. So, but if we order at the minimum point, then we've got this lead time whilst we're waiting for the goods to come in, and we've run out of time. So actually, we order a bit earlier than that, and hopefully, eventually, after this lead time has happened, we've got to this point here, and we get our goods in. And then as we get the goods in, this line goes back up to our maximum, which and this value is called Q here. So it's between the minimum and the maximum is the amount of goods that we're ordering in. And in fact, Q is this variable that we're going to try and figure out. But my point is, as we're going along, let's pretend these lines are parallel. This is what we're going to see as time goes. So the question is, how much is our holding costs going to be for holding this inventory as time goes along? Okay, and the way we work this out is, well, first of all, it's not going to be this value at the maximum times the holding cost for the year, because well, that's not how much we have over the year. Like, eventually, sometimes we have this minimum point. Also, it's not going to be the minimum point because, we've actually got goods. So it's somewhere in the middle. And in fact, mathematically, it's exactly in the middle if we assume... Oops, sorry, I've got a bit close there. If we assume that our inventory is going down at a constant rate. So hopefully you can see that the average amount of inventory we have, along the year is this yellow line. Okay, and this yellow line is represented. Well, we know how much this is. This is Q, the total between the maximum and the minimum. So the average is just half. Okay. And I think that's the reason why is because the area under this triangle here is the same area above the line in this triangle. So, when it's underneath, it's the same amount of inventory here as it is when it's above. Okay, and that's why it's your average is this line, which is, as you can see, half. So it's Q over 2. Okay, so our second formula, which is your total cost, cost of holding, okay, is your average inventory amount, okay, which we've worked out as Q over 2, times the cost of holding for the year, okay, and that is our second equation. So I'm going to write it here, cost of holding, okay. It's quite hard writing with a mouse, so if you think I'm going a bit slow, that's why, okay. 2 times your cost of holding over the year. And these two are the main ones we need to be thinking about. So, just give me a second. So, the main question is, what I'm going to do, I'm going to draw out a graph here. So, the main point is, what amount of Q do we need for this total cost to be as small as possible? Okay, and so this is Q. And remember what Q is. Q is the maximum minus the minimum. It's that amount we're going to be ordering in. So if we imagine Q, right, is really, really small, so we hardly order anything in, what it means is, if we look at this cost of ordering point, that we're going to have to order in absolutely loads, because say the demand's 1,000 and we order 2, we're just going to have to keep ordering and ordering and ordering. Every time you order, it costs this cost of ordering. So the total is going to be, you know, somewhere in the stratosphere, like miles up here, okay? So we can't have a queue that's really low, because we can't just keep buying all the time. You know, thinking about it, because this cost of ordering is fixed every time. So, you know, if it's £5 to order once, then order it 1,000 times, £5,000, you know. So maybe we want Q to be really, really high. You know, why don't we just order once in the year? And if we do that, that's fine for the cost of ordering, because we only have to order once. But the problem is, there's this cost of holding now. And if we have so many goods, and you know, we're paying per year to hold them all, you know, say you buy 1 million and, you know, it costs whatever per unit, you're just paying out your nose. So Q, if it's really large, somewhere up here, it's the total cost is going to be absolutely loads, right? So we can't have that. So actually, the best way to have this total cost to be the smallest is somewhere in the middle, okay? I'm just going to pick a point. I don't know the exact how the formula actually looks, how the graph, but, you know, as we're going along, let's just imagine it's like this, okay? And that obviously should have hit that point. So what we need to look for is, how can we find this point here, okay, where this total cost is a minimum. So, in fact, I'll just write here, just to make it more obvious, your total cost is your cost of ordering times how much it costs to order each time, plus your cost of holding times how much it costs to hold a unit in the year. Okay, so this is our main, you know, equation here. So anyway, so it's this point here, you know, which we've just said. And the way we find this is, if you remember at the start, I mentioned about differentiating and what that actually did. And what it does is it finds what the gradient of the slope is wherever these points are. So if we were to differentiate this equation here, okay, and we put it equal to 0, that would show that the gradient is 0. And if a gradient is 0, can you see, it means we'd find this point, which is the smallest total cost we can find. Okay, so, you know, as you can see, the gradient each time is moving, it's moving, and then it moves this way instead. So to find this point, we're going to differentiate and then work out what Q is. Okay. By the way, I didn't come up with this myself. I found it on the internet, but, you know, I'm just trying to explain it so people understand it better. So anyway, so what we've got is we've got TC equals demand over the amount we're going to order each time times the cost of ordering plus Q over 2 times cost of holding. Okay, so our variable in this case is Q. Okay, so if we differentiate with respect to Q, so do you remember when it was y equals something x plus whatever, right? And we said dy by dx. In this case, it's d total cost, okay? D total cost by dq, okay? Remember, x squared, x, whatever. Now it's in terms of q. So our main problem is going to be this q on the bottom. I knew there was one more thing. So what is q on the bottom? Well, if we go back to our you know, maths tools where it was x squared, and then we've got x to the 1, and then x to the 0. Each time we divide by x. So if it was 2 squared, it's 4. If it's 2 to the 1, it's 2. So we're dividing by 2 every time, and then divide by 2. You know, we get to 2 to the 0 is 1. If we divide by 2 again, or in this case divide by x again, we end up with x to the minus 1. Okay, and that is the same as saying 1 over x, because we're just carrying on dividing each time. So I'll write this up here. To the minus 1 equals n 1 over n. Okay, and similarly, if it was n to the minus 2, it's 1 over n squared, etc., etc. So anyway, so if we differentiate, you know, with this weird notation, this equation here, so and we're doing it in terms of q, so that's like saying I'm going to rewrite this just so you can understand just this part here. So d over q times cost of ordering is the same as saying d q to the minus 1, you know, from our new rule that we've come up with over here. So q to the minus 1 times cost of ordering. Okay, so I'm going to replace, this is what we're differentiating, which is the same as this, and we're doing it in terms of just the q. So we're just thinking about that q variable. So the way you differentiate is you times by the power and then you reduce it. So we end up with times by the power, which is minus 1, times what we've already got, you know, d, and we reduce the power by 1. So it ends up being to the minus 2 times cost of ordering. And then our next part is q over 2, which is the same as q to the 1 over 2, or a half times q to the 1. So what we do is we times by the power, so we've got a half, which we've already got, you know, because this is represented as half times q, right, times q, and then we reduce the power. So the power was 1 originally, so we reduce it to q to the 0, and we know that q to the 0 is 1. So half times 1 times cost of holding, Okay. And that is our, differentiated formula of this total cost. So what does this do? Well, if we've differentiated something and we want to find out what the gradient is at a point of Q, we plug in that value into Q, and then we find out. So on the graph, whatever point at the bottom we plug in tells us what the gradient was. Now if you remember the graph we had, okay, it was something like this. Okay, so we were looking for this gradient here, and the gradient here is 0. So what we do is we plug in, we say, right, we want the gradient, which is the result of this, to equal 0. Okay, so we've got this formula here and we put it equal to 0, and then all we do then is we rearrange this formula to find out what Q is. Okay, so the way we do that, we add this total to both sides. If you've got -1 plus 2 is 0, then you add 1 to both sides, and then you end up getting, this disappears and you end up getting 1 on this side. Okay, or you can say that you move it over to the other side, and as you move it to the other side you swap the sign. So let's use another one. So we've got C to the H, okay, which is this part here, right, and it's times a half, so over 2 equals, so we've flipped the sign, so D. Now Q to the -2 power is the same as saying 1 over Q. Do you remember our rule up here? If it's to the -1, it's 1 over. So if it's to the -2, it's 1 over whatever it is squared. So we get that squared times cost of ordering. Okay, so we're nearly there, and then all we do then is we times up by Q squared. So if we times both sides by Q squared goes over here. We times by 2, the 2 ends up coming here, and then we divide by this cost of holding. Okay, and then the cost of holding goes down here. So if we do all that, we've times up by the Q squared equals, now, and then we times both sides by 2, so a half times 2 is just 1, so that gets rid of it on this side. So we end up with 2 times your demand divided by, and then what we want is, so we've got this part, we've got this, we've moved the Q squared over, we just need to divide by this cost of holding. Okay, and then that is our new formula. And if we square root both sides, we end up having Q equals, cost of ordering as well up here, isn't there? How could I forget the CO as part of the cod over chips? We end up with, so we square rooted the side on the left, so we square root the side on the right, and we end up with 2. Now I'm going to move the CO over here and the D to the end. 2 cod over chips. And that is how much we order each time we go along, to get that total cost to be a minimum when we're thinking of, these 2 points here. So, the total cost of holding your inventory over the year and your cost of ordering as you go along. Anyway, we've made it. Hope you enjoyed it, or at least took something from this.